Okay, so thank you very much for the introduction and thank you for the possibility to give this talk. I won't talk about everything, but about something, some particular aspects I understand. I don't understand enough anyway, but yeah, so maybe it's interesting for you. So, okay, so basically the talk will have kind of mostly two parts. One thing will be, I will try to talk about, let's say, a little bit of a simplification of the model Manuel talked about just in the first talk of this session, and how to implement this on a computer and how to discretize this also in a way which is consistent to the kind of thermodynamic structures which we have on the continuum level. And then also just kind of inspired also a little bit by mentioning of some experimental results from the BEM group in Carsten Reuter's talk. I will also talk about something which we did in this direction, yeah, some time ago already. Okay, okay. So we look just at the generalized Nernst-Planck-Poisson problem, which describes the mixture of a solvent together with n-charged ionic species, which we describe by their concentration Ci and their charge number Zi. And we have a solvent which also has a concentration which we just denote by C0. And basically, charged species move around through to several forces. One is the mixture, barocentric velocity of the whole mixture. And then we have diffusion fluxes, which basically are driven by three types of forces. One is the gradient of the chemical potential of the ideal dilute solvent, so which is basically kind of the logarithm of the concentration, or the logarithm of the mole fraction. We have the gradient of the electrostatic potential, just multiplied by charge number, and here I'm just writing this in molar quantities, so we have the Faraday constant instead of the electron charge. And we have just another term, the gradient of the so-called excess chemical potential, which basically can take into account all kinds of let's say, non-ideal interactions, in particular steric interactions. So we can basically write these Nernst-Planck flux in different forms, which then also give rise to, let's say, different inspirations how to, for instance, discretize them or to just analyze them mathematically. So first we kind of can just see that the, let's say, ideal gas contribution to the chemical potential gradient gives us just the classical Fickian diffusion term, so that where just the movement of species would be just driven by the concentration gradient. We can further, so there are different kind of, let's say, sub-languages in this field. So some people talk about excess chemical potentials, others talk about activity coefficients. And so in this context, activity coefficients is just the exponential of the chemical potential. Yeah? But once we have it, we can also write the very same Nernst-Planck flux in this form, where we just write the logarithm of the activity coefficient times the molar fractions. Yeah? For instance, Stefan Ringe is writing Nernst-Planck fluxes in this way, and so you can have different possibilities here. And as I said, this gives rise to different ways also to treat them mathematically. So I didn't say anything about the excess chemical potential yet. But the, let's say, simplest way to introduce steric interaction would assume that we have just some kind of lattice with a lattice constant A, and which then gives rise to fixed molar volume, which is the same for the solvent, for all other charged species. We assume that just the summary concentration fills up space, which then immediately gives us also limitation of the concentrations, so that we just don't exceed some kind of maximum concentration, which is one of the features of these, which is kind of important if you look also already at equilibrium problems. And then we can introduce the ideal gas chemical potentials for all species, including the solvent, and calculate the solvent concentration from the incompressibility constraint. And this gives us rise to, and we assume that the excess chemical potential is just the negative chemical potential of the of the solvent, and which then depends on all the other species in this kind of term, and this is the equivalent activity coefficient here. Yeah? So this approach is basically known since the work of Bigerman, and there are many papers who just from independent angles introduce these possibilities. One is the paper of Bohrhoff et al., which is quite known about this, but yeah, so Bigerman was, I think, the first who did something like this. And then we can try to improve this model. So this then basically gives some interpretation of Manuel Landsdorfer's talk. So we introduce molar volumes. Ions can now have different sizes. We introduce molar masses and relative molar masses. We basically can assume that the ions are solvated. That means the volume which goes into our model basically is the solvated molar volume. And this goes also in the incompressibility condition here. And this then means that so we also have a non-constant summary concentration anymore. So if we write these molar fractions, we need to be aware of that this C bar then depends on all other concentrations. And the, let's say, kind of main contribution then also from this work of Dreyer et al. Is the fact that once we derive these chemical potentials from the corresponding free energy functionals, we need to take care of the pressure. So because if we have, let's say, exchanging volumes, then we get an influence on the pressure. And that means that our excess chemical potential, which we just can calculate from in this way, basically will, in addition to the concentrations, all the species concentrations will also couple to the pressure. Yeah? So this is, let's say, the excess chemical potential or the corresponding activity coefficient, which comes from this theory. Basically, the barocentric velocity of the mixture would be calculated by the Navier-Stokes equations. It is kind of interesting when one thinks about implementation also into numerical methods. There are kind of Stokes solvers which are kind of around. In many cases, just assume that the density of the fluid is constant. So we can just make a submodel here where we just assume a constant density case, which basically has then the same relation of where the relative molar masses are equal to the relative solvated molar volumes, if you can call it like this, and we get another form of the excess chemical potential, which then, by the way, also is independent of the pressure. Yeah? So it would be interesting then also if one would implement Navier-Stokes equations, one really needs to be careful to work also with non-constant pressure conditions. So, in many cases, of course, we want to talk about the mechanical equilibrium, but then still mechanical equilibrium means that this part of the momentum balance with the Coulomb force remains, and this gives us this kind of differential equation where the gradient of the potential is balanced by the charge density times the electric field. In order, there are different ways to handle this numerically. So what I'm kind of thought about, and what I'm doing here also, is that I take the divergence of this equation, which you can where you just kind of assume that the density gradient and field gradient and electric field are kind of parallel. Then we have a nice second order PDE, which can also get kind of boundary conditions, and then which then can be implemented standard finite element, finite volume methods. Okay, so if you look at the thermodynamic equilibrium, we basically can integrate the Nernst-Planck fluxes. We set them 0, give bulk reference values for concentrations and potentials and pressure, and which then also give rise to the bulk values of the activity coefficients. And then we can basically, for instance, can have this expression for the concentrations which is an algebraic system which couples all the concentrations. Yeah, if we write it in this way. And we can combine this with the Poisson equation and the momentum balance. So in this case, where we write it in this general form, we have these two PDEs and just the corresponding ordinary algebraic equations which describe the concentrations, and all this needs to be solved together in a consistent way. We can also, once again, simplifying the model and assuming that all molar volumes are the same, we can introduce the activity. We can express the activity coefficients in activities, and then everything collapses to the kind of well-known generalized Poisson-Boltzmann system, where we have this activity of the species on the top, and then the 1 plus molar volume times the sum of the activities of the species in the denominator. And if, so the gamma would be 1, then we would go back to the original Poisson-Boltzmann or Gould-Chapman model. And if we set up now a computational domain, which would mean some kind of double layer, some ideally polarizable working electrode, we can set the electrode side, a working electrode, apply potential, and just corresponding no-flux boundary condition for the pressure, and some bulk boundary conditions. We get the Poisson-Boltzmann double layer capacitance curves. We can, with the ideal mixture or the Biedermann model, we see this camel shape, and we can go down to realistic experimental values if you just introduce the solvation mixture by the model of Dreyer, Gulke, Müller, Landsdorfer. So this was essentially Manuel just quite a bit talked about these things. Yeah? So the different colors in the curves gives rise to different molar concentrations here. Okay, so I just wanted to talk also about how to implement this. And so one favorite method for doing this is the finite volume method, which is quite successful discretization approach, for instance, in semiconductor device simulation. And the nice thing is that compared to the finite element method, so this is a kind of infinite discussion, of course, between numerical analysts, what is the better method. Yeah? But the finite volume method basically does what is consistent to what we do when we derive these partial differential equations, where we see, okay, so we have some representative elementary volume, we have the surroundings, and then we look at the exchange between the volume and the surroundings and take up Gaussian theorem, and then we can set up the partial differential equations. Here we do the following: we just kind of construct artificial representative elementary volumes and do just go back this derivation of the PDE to the derivation of a discretization system. Yeah? So that means we can use the triangulation of the domain, so-called Delaunay triangulation, which shall have certain properties, which allow us to take the circumcenters of the triangles to connect them, and this gives rise to the so-called Voronoi cells, which contain then, each Voronoi cell contains one of the edges of this triangulation. And the nice feature is that by the very construction, the line coupling, the collocation points which we use for our discretization is orthogonal to the interface between two neighboring cells. And this means we can consistently discretize, calculate the fluxes between neighboring cells by just taking finite difference approach ansatz for or finite differences between these values in the collocation points. Yeah? So this is the kind of important feature. The method has been also already found in the 50s. And as I said, is quite ubiquitous in several fields, including semiconductor device simulation. And then we can just discretize this. So what we do here, we take some control volume or representative elementary volume or finite volume K. We integrate over the equation over this, then we can take the Gauss theorem, cast the divergence to a surface integral. Here we just, and then we use some, let's say, a kind of quadrature approximation, where we just take the value from the collocation point to approximate this volume integral. And we just look at the size of this interface, multiply this by the, in this case, local electric field projection, which we just take from finite differences. And this gives us, in the simplest 2D case here, the very same discretization, by the way, as we would do with finite elements. In 3D, it's a little bit different. And this is just for the Poisson equation. So, and for the Nernst-Planck flux, we really once again look to semiconductor device modeling. So where the so-called Schaffer-Gummel scheme, which is the kind of naming of the scheme in the semiconductor field, but it's also well known as the Ilien scheme by numerical analysis, and an Alan-Southwell scheme by also just fluid people from fluid dynamics, and it's also, I don't have it on the slide, it's also known as John Cooper scheme by plasma physicists. So everything found seemingly found independently. And here this is some upwind link, which means we have, this is basically in this, we have this compared to what we have in Poisson equation, we have this kind of strong convective terms which come from the gradients of the electrostatic potential. And just basically numerical analysis 101 says we need, if you have this situation where we have this convective parts, we need to do so-called upwinding in order to stabilize the discretization and to guarantee that, for instance, concentration don't get negative values. This can be done by upwinding, and this scheme basically is a particular exponential fitting upwinding scheme, which kind of takes into account the need for artificial diffusion, which is a reformulation of upwinding in such a way that it's just minimized in such a way that we just get this stable scheme. So there are other upwinding schemes which do this in a more coarse way. And the nice thing about this ansatz is also that, as we also will see, that this also has nice thermodynamic properties. Yeah? So, and then we take, so if you look at the semiconductor device textbook, then we get the scheme without the red terms, which take into account just the differences of the electrostatic potential in these so-called, as the arguments of the so-called Bernoulli functions, which describe our upwinding. And then the simple idea, if you look at this drift diffusion form of our Nernst-Planck flux, is then, okay, so let's just add to this the gradient of the excess chemical potential, and that's it. Yeah? So, and this, okay, so it's a nice idea, which I also figured out, and then, but we have seen, okay, so, yeah, semiconductor device people did something also for Fermi statistics already in 1988, and Liu and Eisenberg also found the very same scheme and published this in their paper from 2014. And that's now the kind of, we try to use this as the kind of working horse for our discretization ansatz. With my French colleagues, mainly Benoît Godel, we analyzed this scheme. So as every finite volume method, it has this exact local and global charge conservation. So we can, this is one of the nice things of the finite volume method, that we can really have these conservative properties which we have on our continuum level. We have consistency to thermodynamic equilibrium. So here the point is that we could just discretize our nonlinear Poisson equation, as I showed it to you, yeah, independently of the Nernst-Planck system. And then on the continuous level, we kind of can show that if you start with some initial value and get a time evolution, then at some point the system will drive into equilibrium and give us the solution. So the Nernst-Planck system will then at equilibrium give us the solution of the Poisson-Boltzmann problem, or generalized Poisson-Boltzmann problem. And here we can prove that this is also true for the discretization, which is not completely obvious. With finite elements, for instance, it wouldn't be like that. Yeah? So that's just another selling point of these methods. Then we can also show that the concentration stay within the limits of natural constraint. We can find the counterpart of the free energy on the discrete level and the discrete dissipation rate, which then tells us the that we have a decay of the relative free energy along the solution trajectories, like in the continuous case. Then mathematicians are also, of course, always interested in the existence of solution of the discretized system, and we also have weak convergence of the discrete solution to the continuous solution. Yeah? So this is, so in that sense, quite nice. So selling point of the scheme, and we also did can show some numerical experiments with this. So this is once again a one-dimensional problem, and the symmetric cell, where we basically in the one-dimensional domain apply just fixed voltages at just time equal to 0. And we assume that we have just constant positive and negative ion concentrations, and correspondingly this gives rise to, just from the compressibility condition, gives rise to also to a concentration of the solvent. And then we let time evolution go, and we get a redistribution of the ions. We see here the corresponding boundary layers of the positive ions, of the negative ions, just depending on the applied potential. This is the electrostatic potential here. Yeah, we also get these potential boundary layers. And we can see how the discrete free energy also decays exponentially. And we can also see the dissipation rate per time step. And for this kind of simulation, we also use the idea to use the dissipation rate as the kind of control parameter for the time step size. So this is kind of consistent to what has been shown theoretically. And we made another experiment where we have a so-called ionic diode, electrolytic diode. So in a semiconductor diode, we have doping, which kind of separates the positively and negatively kind of doped material, which gives them fixed charges and gives rise to the rectification behavior. And the equivalent of doping here is that we have opposite surface charges, which are just a part of the boundary conditions for the electrostatic potential. So these are two-dimensional domains, and the channel goes just from top to bottom. And then we can just apply a potential over this domain, and then we can have a forward bias with high ion concentrations and a reverse bias with lower ion concentrations, and this is kind of controlled by these opposite surface charges. And from this we see some, in this example, not very strong, but rectification effect. So and we also did convergence experiments, numerical convergence experiments for how accurate is this IV curve, and we see a second order convergence rate. So this means that our scheme, discretization scheme works well. Yeah. So, another thing we worked on is the coupling with electroosmotic flow, where we then basically get a Nernst-Planck, in the first approximation, Nernst-Planck-Stokes system. And Alexander Linke and Christian Merdon at our institute basically developed so-called pressure robust finite element methods, which provide a way to discretize Navier-Stokes equation in such a way that we get a pointwise divergence-free discrete solution, which then just in a consistent way can be coupled to the finite volume method in such a way that we get a finite volume equivalent of the divergence condition, which just can guarantee that we have these maximum principles and stability of the solution of the transported species. And we just generalize this. Basically, the trick is we generalize this discretization ansatz by just introducing the projections of the velocity onto the discretization edges into the arguments of the Bernoulli function. This would give us the upwind discretization then for this coupled system, where we also would have the barycentric velocity. Yeah? And some experiment then is some, let's say, calculation of electroosmotic flow So this is some channel with a charge on one of the sides. Here we have in the middle have a symmetry boundary condition. And if we apply an electrostatic potential along the channel, then we get just the body force acting in the boundary layer where we have the polarization effects. And the body force then drives the solution into one direction. Yeah? So, and that's the kind of this electroosmotic flow effect. And this gives us some kind of, normally in channels, if you see flow in the channels, it's Hagen-Poiseuille flow, but here we get some kind of plug flow because the force is already only in the boundary. And what we see from this simulation is that if we just, let's say, use, instead of the classical Nernst-Planck model, if we use the improved or generalized Poisson-Boltzmann model for calculating the Nernst-Planck part of the system, then we see an increased flow velocity just because of the fact that we get wider boundary layers due to the concentration limitations. Yeah? So that's some kind of effect which we have seen from this type of simulations. Okay, so this all assumed that we don't have reactions. Now let's try to introduce reactions. And okay, so I will see how much time I will have for this. But basically, the idea is here that there are also a couple of papers of Wolfgang Dreyer and also Manuel Landsdorfer and colleagues, which try to introduce surface reactions also in a thermodynamically consistent way. And one of the postulates is that we have reaction rates for the electrochemical reactions, which basically depend on the chemical potentials at the interface between solid and the metal. And that means that we take into account the chemical potentials at the metal side of the electrode. So this zero is kind of a mistake on the slide. And we, just for simplification, we can assume that the surface chemical potentials have the same values as the chemical potentials of the soft species at the interface, or in the mathematical sense, the trace of their chemical potentials, by assuming that we have fast adsorption. You know, so this is what I will assume just in the sequel. Yeah, and then we just can have, let's say, these corresponding reacting species. And this chemical reaction equation, we can introduce the affinity, which takes into account the chemical potential and the kind of differences in the stoichiometric coefficients. And then basically we postulate a rate expression which takes the experimental terms in the affinities and the symmetry coefficients beta as the rate expressions at the interface. And then we can just look at these expressions. For instance, if you assume, okay, we have a just simple redox reaction, yeah, where we have the species R and O with this kind of simple chemical reaction, then this would be our affinity. Here we would also introduce the chemical potential of the electrons or the work functions as a parameter in this affinity term. So they basically take part in our reaction system of species number -1. And then we get the surface rate expression. And this would be then the fluxes which occur in the boundary condition for our Nernst-Planck equations. And in addition, we can also introduce the inert background electrode, where we then have a species S and X, which are concentration numbers 3 and 4. And this would be, we can look at this at the scale of the Nernst-Planck equation. But then, of course, if we look at the sizes of experimental devices which electrochemists use, then basically this is at a size where basically everything which is happening in our polarization boundary layer is happening on a spatial scale which is much smaller than the device width. So it's nearly impossible to take this into account if one wants to solve this numerically. So people basically work with the assumption of local electroneutrality. And this means that just our Poisson equation turns into just algebraic equation. We then can multiply our Planck's equation by the respective charge number. And then we basically the time-dependent part and the part depending on the velocity disappear due to the electroneutrality condition. And we can see that we have an equation, another equation, which for the electrostatic potential, which is now Ohm's law, often mistaken for Poisson's equation, and where we here have the conductivity sigma as the parameter, and not the electrostatic permittivity. And we also, in many cases, just this contribution is assumed to be small. For instance, if you can assume that the diffusion coefficients are, and the concentration gradients are not large, and so on. So basically, this approach leads to the fact that we can reduce our species transport just to the convective diffusion equation, where we have the convective term from the electrolyte flow and just the diffusion part remaining from the Nernst-Planck equation. And yeah. And one important thing is in this, when we want to reduce this, is also the fact that the background electrolyte concentration is large enough so that this one dominates the conductivity. And if the conductivity is large enough, basically the electric field in this electroneutral domain is essentially zero and can be also ignored. Yeah? So that's what people are doing. So if we motivated by asymptotic analysis, one can just back this also in a mathematically more rigorous way. So this is in the paper of Dreyer, Gurke, and Müller in 2015, and also in the PhD thesis of Clemens Gurke. So basically, one can derive these electroneutral equations, and the fact that we can assume an equilibrium in the polarization boundary layer by asymptotic analysis, and just the method of matching asymptotics at the interface between the double layer and the bulk. And this allows us then to define chemical potentials at the surface by the values of the chemical potentials in the electroneutral domain. Yeah? So that means that the chemical potential at the surface has the same electrochemical potential at the surface is the same as the electrochemical potential at the interface between the double layer and the bulk electroneutral domain, where everything is already electroneutral. And then we can calculate the surface chemical potential from the chemical potential at the bulk side of the double layer plus the difference of the electrostatic potential over the polarization boundary layer. Yeah? And this can be so then we have kind of two ways to look at this system. We would have the nanoscale, where we have our boundary layer resolved. And just we have this, let's say, I call this experimental cell scale, where we assume that we have the electroneutral bulk, where basically everything what's in the double layer collapses into a boundary condition, and we get new interface condition and jump of the electrostatic potential by the size of the applied potential. And this gives us, in a way, a term which can be then, let's say, reformulated into something resembling a Butler-Former equation. So we can then take our ansatz with our affinity for the redox reaction, but just at this term, which takes into account the jump of the electrostatic potential of over the double layer, reformulate everything, and then we get a term which very much looks like one version of many of the Butler-Former-like equations. Yeah. So, and then that's what then experimentalists basically then do. They have this convective diffusion equation, have just some bulk boundary conditions and have then just the reactive boundary conditions where we have, which are, let's say, Rorbaum boundary conditions with the flux terms. The potential start controls the counter electrode in such a way that a well-defined potential between the metal side of the working electrode and some reference electrode is maintained, and the value of the potential in the reference electrode basically corresponds to the potential value in our electroneutral domain. Yeah. So, and if with a well-supported electrolyte, you can place it somehow close to the electrode and assume that it's constant, and we get this potential jump for our calculations. Yeah, and then we get this Butler-Former rate equation, and this is the way we can just make the link to electrochemical experimentation. So what I did is I tried this out, how this plays out, this kind of asymptotic transition from the double layer scale to the electroneutral scale. So the green, so this is basically, these are applied potentials. This is static voltammetry, so it's just stationary solutions over calculated for every of these potential values. The green curve is our electroneutral model with the Butler-Former equation, and the red curve denotes the model with the fully resolved boundary layer. And we see that at least for a reasonable small potential range, they really exactly match. But we get then, of course, other effects if we just increase the potential. So in particular, we get Coulombic interactions, which are not part of this let's say, collapsed double layer model, which then basically lead to a decrease of the reaction rate if we further increase the potential. And there are some people who call this so-called Levitch exclusion in the literature. And this is something which is seems to be seldomly mentioned in electrochemical experimentation, but I have seen mentioning in this in papers by the Compton group. So this is some effect which basically at larger potentials kicks in, and would be kind of interesting also to see more about this and to discuss this more. At very large, larger potentials, so these are always the same calculations, but on a different, let's say, zoom scale of the y-axis. And here we see, for the electroneutral case, of course, then also the diffusion limitation kicking in. Yeah? So in our domain. Yeah? So that's something which I'm still interested in discussing. Also, maybe we can also discuss electron spillover and how this goes into this model. That would be interesting to discuss here. Okay. Just also inspired, so some earlier work before I worked on this Poisson-Nernst-Planck stuff involved just modeling on this kind of electroneutral scale of limiting current experiments and some other reactive experiments. So we could imagine that our hydrodynamics, our Navier-Stokes equation, can be solved easily in a thin layer flow cell. So that's not returning disk electrode, it's the wrong label here. So why I do have it there, I don't know. So it was a bug when I made the slides. So this is Hagen-Borsell flow, and just this is a through flow cell. We have some catalyst layer. We basically can measure assume that we have some reactive species. In particular case, it could be, for instance, just hydrogen, which is injected at a given rate. It reacts at the catalyst site. And we can measure the reaction rate as the current, and as the anode current, and we can also measure the product composition at the outlet. So this is of some kind of flow cell setup, which then exists in different versions in different labs of electrochemists. And here we use the convective diffusion equation just for in this case, hydrogen species in order to describe the transport. And the particular thing is that we assume that we have a zero concentration at this catalyst layer, which means that the electrostatic potential is chosen in such a way that the reaction is fast. So we get the limiting current, which we then can measure just as the flux over the species through this boundary condition at the anode. And we did this experimentation and compared this with experiments in the BEM group. And so there's the theory by Levesque in 28 1928, that the limiting current is proportional to the third root of the velocity. So this can be derived by asymptotic theory. But the tricky thing is that this is only true for large velocity. This is a large velocity asymptotic. And when we compare to these experimental values, we see that basically, so these are log-log plots of the Sherwood number, which is proportional to the current. So the straight lines give the asymptotic values, but we see that we have deviation for smaller Peclet numbers from these asymptotic values. And this means that, in fact, the cell height correlates with the size of the hydrodynamic boundary layer. Yeah? So, and we have seen, and that was important when we tried to interpret these measurements, that part of the measured values basically lie in the subasymptotic part. Yeah? So that means that kind of, in order to understand this, for instance, one can use, we have the dependency of the diffusion, the limiting current on the diffusion coefficient. You can use this experiment, for instance, to measure diffusion coefficients. It's kind of important when you interpret it in this way. And the fact is that basically, depending on the flow rate, we see that for small flow rates which have been used in the experiment, we cannot use the asymptotic theory because just the, let's say, hydrodynamic boundary layer is too large and it just correlates with the domain size. But for larger velocities, then we see that this boundary layer is smaller. Another experiment which has been made by the Behm group, which was mentioned also by Carsten Reuter in his talk, and that's why I'm also just trying to talk about these things, is just the multi-stage reactions, where we, for instance, have oxygen adsorbing reacting on the surface to hydrogen peroxide and then to water and desorbing. And we can get also desorbing hydrogen peroxide as some intermediate product. And the question is, how large is the share of the intermediate product just in the overall reaction products? Yeah? And the measurement says that with increasing catalyst coverage, the share of this intermediate product decreases. And also with increasing electrolyte velocity, the share of the intermediate product increases. And this, there's another experiment also with formaldehyde, which is similar, which just relates then the rate of the intermediate product also to the catalyst, loading of the catalyst. And this raised us to make just this type of experiment with this kind of reaction boundary conditions in two variants. One would be just that we have one large catalyst error with a given length, or just amount of catalyst spots, which then would just kind of, let's say, interoperate by and just where we just species could desorb at one spot, are transported to the next one, could react again, and so on, and this could go. And we assume here that we have constant temperature and also constant potential. So in that sense, it's not a completely electrochemical experiment. And also we assume that we have stationary conditions. Yeah? So then we can model this once again. We have then three species. This is kind of in a more expert setup, three species, A, B, and C, which are all transported by this convective diffusion equation. Then we have corresponding inflow boundary condition, outflow boundary condition, and reactive boundary condition at the catalyst interfaces. We can measure the outflow of the species, and we can also we can measure the relative amount of reaction intermediates by just taking the amount of species at the outflow over the summary outflow of the products. And then we can model this in such a way that we have our dissolved species. They can adsorb to the catalyst surface and react on the catalyst surface from A to B to C, and of course then also desorb. And if we would have a fully electrochemical experiment, we would also just have the corresponding reaction to protons and electrons and the corresponding current, which we ignore in this case. This can be then described by rate expressions, which take into account the fraction of the free catalyst site. So the idea is to just assume that adsorption is a reaction with a free catalyst site, and which then results in a catalyst site which is just, for instance, species A reacts to theta A, which is then species A adsorbed at the catalyst. And yeah, so this is, yeah. And then we can have another parameter here, which is catalyst loading. Then we can set up the corresponding evolution equations also for the concentrations of the adsorbed species, which would be part of the system, which in the stationary case then reduced to an algebraic system. And we, yeah, then can use our finite volume method and discretize these things and can do the calculations. And we see very much the same effects where we have just the relative amount of the reaction intermediates, the blue curves decrease with increased catalyst concentration. And it increases with increasing flow velocity. So, yeah, so that means from this kind of relatively simple modeling, which then includes the connective diffusion transport, we can see already the effects which had been found in the experiment, which then can partially at least explain what has been measured. We have, yeah, so and then, yeah, so with the simulation approach, we can also work on different flow cell geometries. We had some cooperation with Helmut, with the Baltuschat group in Bonn, where we did Navier-Stokes solutions for their flow cell, also then coupled to species transport, and then we can see that we don't have this kind of really third root dependency on the flow rate for their flow cell, but we can still take a look at the limiting current and compare it, and then for instance match this to the cell height, which was a little bit unclear by the construction of the cell. And part of this story with hydrodynamic coupling, hydrodynamics, transport, and reactions is of course the rotating disk electrode. We discussed this in one of these working groups over here. So these are our things which also could be just modified by numerical simulations if we would have more complicated situations here. And yeah, so that's mostly what I wanted to talk about modeling method-wise. Just two more things. How to implement this. So from this finite volume method, basically for this kind of system of coupled reaction diffusion convection partial differential equations which can describe a certain class of problems, we can derive just a discretized version for the finite volume method. So where we just have our storage terms, our reaction terms as functions in our model, and we just have the fluxes between neighboring control volumes as another function, which then depends in this case on these two variables. And this would be just the discretization of our system. So we all have this describes a system of n coupled species. Yeah? And then we can solve this. So this gives us the discrete nonlinear system for the coupled species. We can solve this by Delaunay mesh generation in order to get these Warner meshes, implicit Euler time discretization for stability, Newton's method with analytical Jacobians in order to get a highly accurate solution of this discrete system at just reasonable effort. And then we need to solve the linear systems. And these are, for this we can use various direct and iterative linear solvers. All this can be formulated in such a way that we have physics described by these functions and the geometry described by the grid. And this can be just written in this way also for 1D, 2D, 3D problems. And we implemented this now in the Julia language. Just one thing to mention why we did this with Julia. One thing in Julia is that we have very easy access to automatic differentiation. And that means when we want to create the Jacobi matrices for our Newton method, we just do this by automatic differentiation. Yeah? So we don't have to write the complicated code for these complicated nonlinear models just by hand. Yeah? So which we did before in our C++ Python version, was a kind of mess of a work. And So for instance, this would be just now, just in a simplified setting, but our kind of Nernst-Planck flux. This is the function you have to write for the model where I showed you the simulations. Yeah? And this can be autodiffed and put into the local Jacobian from this function which we get can be put in the global sparse matrix, and that's the way we generate Jacobi matrix for automatically generate the Jacobi matrix for our simulations. So if you want to try out nonlinear models, we just use this approach. We can vary whatever parameter, introduce nonlinearities. Everything is handled by automatic differentiation. Yeah? So tomorrow we will also have another talk about automatic differentiation by basically two talks, which will mention this, Michael Herbst and Rachel Curtin. They will talk about this in the context of molecular simulations. Yeah? So, and this is part of a larger effort which we are doing, where we develop a couple of packages for PDE solution. Also, we just to mention external FEM, which implements this pressure robust finite element methods I talked about, and also try to make this compatible to the larger Julia SciML infrastructure with the kind of really good ODE solvers, the linear system solvers. And this is also kind of interesting work we are doing. And one thing which, for instance, is allowed by this is for this the fact that we can use symbolic tools which Julia has as packages. There are two packages, modeling toolkit.gl and then the catalyst.gl, which allow to take into just, for instance, reaction networks which one describes in a domain-specific language as chemical equations, where you just specify just the equations with the arrows and the rates, and catalyst.gl can turn this into a reaction system by just applying, let's the rules of mass action law. And then we can get reaction functions which are generated symbolically. And for instance, we can just use these generated reaction functions as callbacks in our Voronoi finite volume package. I have an example on this. This is also just open source. Yeah? And then you have a way to get from chemical reaction descriptions to the just reaction terms in the PDE. And we try this work together with Stefan Ringe and his master students and PhD student are just presenting a poster by Chun, Mas, Sol, Fuhrmann, Ringe. One of these workshop posters basically uses this approach to take the Python-based description of the reaction network in the CatMap code, which had been developed by Ringe et al., and to kind of turn this using the symbolic tools into Julia functions, which can be taken as the reaction functions at the interface between metal and electrode in our finite volume solver. Yeah? So that's something which is work in progress. So we have just kind of first results. So this is the paper from Ringe et al. From 2020, the red points where this same problem has been tackled using Python and coupling to COMSOL. And here we have just the overall, let's say, monolithic coupling between reaction, diffusion, and all these transport things in one large system. And we have one Newton method for everything. And we can do these calculations in a significantly wider potential range. And we are just working on just really releasing these things in a good way. Yeah? So. Okay, yeah, so let me come to conclusions. So as already Manuel tried to say, thermodynamics informed generalized Poisson-Nernst-Planck models are able to reflect quite accurately experimental data. And we have shown this for the equilibrium. We are trying to work on this also for just, let's say, the reactive simulation situations. There are also mathematical consistent ways of upscaling to the electroneutral scale, which is basically the modeling scale which is used to interpret experimental devices. Fluid dynamics then becomes important. The Julia language provides an open source environment in order to implement efficient reproducible solvers for these complicated nonlinear models. And the one important thing is really the possibility to use automatic differentiation. And we are trying to use this in several projects. We have another project on ion channel modeling, which also uses the very same electrolyte model. we have a semiconductor modeling project which uses these Warner packages, which is quite similar, which has very, let's say, similar discretization approaches, flow and post media, and so on. And yeah, okay, so that's it. Thank you.